Well, welcome back, and we're going to start looking at some of these calculations that we were talking about in regards to relative atomic mass. Now that we know what it is, we're going to start looking at how we actually calculate it using values from a mass spectrum and from the periodic table. So for our first example here, we're looking at magnesium. So from this, we can see that we've been provided data rather than a mass spectrum. So in this case, we've been given data for each of 3 isotopes of magnesium, magnesium 24, 25, and 26. We've been given the actual relative isotopic masses, so the exact relative mass of each isotope, along with their percentage abundance, and this would have been obtained from a mass spectrum. So if we want to calculate the relative atomic mass, we need to remember our formula that is the relative atomic mass is going to be equal to the isotopic mass, so 23.99 multiplied by its percentage abundance, which is 78.70, plus that for the next one, 24.99 multiplied by 10.13, plus, I'm running out of space here, sorry, 25.98 multiplied by 11.17. So we're going to add those, do those sums, add them all together, and then we're going to divide the whole thing by 100. When we do that, we will end up with the relative atomic mass. And you can see from here that we can see that when we do this, the 23.99 times 78.7 and our 24.99 and our 25.98, adding those all together and dividing by 100, we get the relative atomic mass of 24.31, which if you actually have a look at the periodic table will be correct. It is important with these, particularly when you're looking at the exam, they usually change the values ever so slightly so that if you've done the calculations correctly, you won't get the value that is printed on the periodic table that you're provided with in the exam. This is so they can avoid, if you just write the value from the periodic table, they know that that's what you've done rather than the calculation. So it is important that you do these calculations rather than just going, oh, hang on, I can get that from the periodic table, if it's asked you to calculate the relative atomic mass. There are times, like in the examples coming up, where we'll need to look at the periodic table to get that value in order to solve for the relative abundance. So this is an example where we see that we've been given a mass spectrum. So this one here, we can see we've got the mass to charge ratio and the percentage abundance given on our y-axis. So this is a mass spectrum for germanium. Okay, and we can see here we have 1, 2, 3, 4, 5 isotopes of germanium being shown in this one. We've been asked to write the formula for the nuclide symbol, so the standard atomic symbol, for the heaviest species of germanium. So we're going to look for the peak that is furthest to the right, because that will have the highest value on our x-axis. So this one here, which is 7.6%. And we need to look at our axis along the bottom here, and we can see that along our axis we've got 75 to 80, and then we've got 1, 2, 3, 4, 5 gradations. So this must actually be a mass number of 76. So in this case, we would be able to write our symbol as germanium. And then it's going to, when we look that up on the periodic table, we will find that germanium is element 35, so its relative, so its atomic number is 35. It will have 35 protons, and then its mass number is going to be 76, because we can see that from its mass to charge ratio on the mass spectrum. One thing with these is to remember, because it has shown a peak on the mass spectrum, it must be a positive ion. So we're going to give it a charge of +1 by showing it with a positive ion, because that shows that this is the species that is shown up on our mass spectrum. Okay, so now it wants us to use the percentage abundance of each isotope to calculate the relative atomic mass of germanium in this case. So this is going to be done in exactly the same way as what we did the previous one. So have a go yourself. So pause the video, have a go yourself, and then come back to see the solution. Well, so hopefully you've managed to pull this information out of the mass spectrum so far. So what we have here is that we've taken each of the peaks, so this one here, the 20.6, and then multiplied that by the mass that it corresponds to. So we've got 20.6 multiplied by 70. Then we're adding 27.4 multiplied by 72. Then 7.7 multiplied by 73. 36.7 multiplied by 74, and 7.6 multiplied by 76. Then we're going to add all of that together, and this will give us a total of 7,270.3 if we use our calculator. So then remembering that we need to divide this by 100 because we need to divide by the total percentage abundance, which is 100%, and we will get 72.7, which is the relative atomic mass of our germanium species, which, remembering, this is the weighted average of all the isotopes and their percentage abundances for this element. Okay, so now we're going to look at one of the last types of question that we need to do. This one's a little bit trickier. We need to get a little bit of algebra going in order to solve these types of questions. So here we can see that it's talking about lithium, and we're told the relative atomic mass. So we actually have AR here, okay? This U is being used for relative atomic mass, or AMU, at this stage. So it has two naturally occurring isotopes, lithium-6 and lithium-7. Okay, so their masses then were given here to 5 significant figures, so 6.051 and 7.0160 respectively. In this case, however, we've been told that we don't know the percentage abundances, so we need to find the percentage abundance. This is where we need to use a little bit of algebra. Because we know there's only 2 isotopes, we can say that let the percentage abundance of lithium-6 equal X, and because we know that they add up to 100, then we know that the other one, the percentage abundance of lithium-7, is going to equal 100 minus X. Okay, so now what we can do is substitute these into our relative atomic mass equation and solve for X. So if we look at it this way, we get AR is equal to, so our lithium-6 isotope is going to be 6.0151 multiplied by X, plus we're going to now have 7.0160 multiplied by 100 minus X, all divided by 100. Okay, we can also, because it gave it to us in the question, substitute our relative atomic mass now for 6.941. When we solve this, we can then multiply both sides by 100 and get 6,941 is going to be equal to 6.0151x plus, and then we're going to multiply out across our brackets. So we will get 701.60, and then we're going to get minus 7.0160x. When we collect our like terms, what we will find is that x is going to equal 7.49, and if this is the case, we can work out what 100 minus x is going to equal, which is going to be 92.51%. So these will actually be the percentage abundances of each isotope. Okay, and this is the more complicated example of how these can turn out. The important thing with these is remembering that when we're talking about percentage, it must add up to 100. So if we've got the two isotopes, we can use a simple algebraic form to be able to solve for them. And now we will do a bunch of practice on these the next time we meet up in class. Okay, so just a quick note, because I know a couple of you on one of the worksheets that we were looking at were struggling with a question in relation to yttrium and strontium as to how we would separate them. The properties of isotopes, okay, because they are the same element, okay, we're talking about exactly the same element, they're going to differ in the number of neutrons only, because neutrons don't change the way that the nucleus is structured in terms of its charge or the number of electrons, so therefore the way it reacts. They're going to behave in exactly the same way. Okay, the only way they differ is they have different mass numbers, but they have the same atomic number. This means that they're going to have the same number of electrons, the same electron configuration, so they will have the same chemical properties. Okay, so we can't do anything to them chemically to be able to separate them out. So the physical properties such as density will differ, but only slightly, because 1 AMU is not very much at all. Okay, so this means that we can separate isotopes from each other when we look at things like the enrichment of radioactive uranium and things like that for nuclear programs based on mass, but mass only. We can't separate them based on any chemical properties because they're dependent on the electron configuration. Okay, so hopefully this is your checklist of ideas for week 1 and 2. Okay, so you need to be able to describe the nuclear model of the atom, outline the structure of the atom in terms of its dense, small central nucleus and orbiting electrons, describe the essential properties of each of the subatomic particles, how the atom is considered electrically neutral, and then be able to describe the difference between ions and isotopes, as well as looking at isotopic mixtures and calculation of both AR from percentage abundance and percentage abundance given AR and the relative isotopes. So hopefully you can do all these things. Make sure you make a checklist of anything that you're unsure of, and we can go through that in class.